fine if you. I mean, you guys just pass these.
Okay, let's go ahead and get started. Oh, I need one of those, though. Can I get one of those? Thank you. Thanks, I'll just borrow it. Okay, welcome to quantum field theory. So currently, oh no, it's missing the second page. Are these double-sided? They're supposed to be, oh, they're 2 pages. They didn't print double-sided. Okay, sorry about that. Some of you got double-sided ones. Okay, the lucky ones of you got double-sided. The ones of you who didn't, I wasted paper by accident. Sorry about that. Anyway, you are currently being passed around a syllabus. Before I begin with the physics, I just thought I'd go over some useful information on the syllabus. So let's just go through some of the administrative stuff. This is Physics 610, quantum field theory. We meet twice a week for a very long time. So this is a 2-semester long class, 20-something lectures this semester, 20-something lectures next semester. We meet Tuesday, Thursdays. You've probably figured out where we meet. One warning, I am going to have to miss a couple lectures throughout the semester. So for example, next Tuesday, unfortunately, I'm going to have to miss a lecture, and then again another lecture in October. So sometimes when I miss lectures, what I'll do is I'll try and arrange for someone else to talk instead, usually about some special topic or something like that, just sort of more fun. I will also, however, try and do some makeup lectures. So probably, most of you are graduate students, right? Am I correct in understanding that? So probably the easiest thing for us to do as far as making up lectures that I have to miss is just to go for another week or so at, into the exam period at the end of the semester. Because officially, the last day of lectures is, I think, December 3rd. But most of you, if you're master's students, are not taking exams. Am I correct in understanding that? You don't know. You have no idea because you just arrived here, so you don't know what's going on. What's that? One course has an exam. Okay. So one thing we could do is we could extend a class or two into the reading period if we need to. I think we may only have to make up one class. The other thing we could do is not have a makeup class, which I guess is okay. But there's a lot of stuff to cover, and if I want to do the material justice, I need to, be a taskmaster and give as many lectures as possible. The other thing we could do is just find some other time to make up a lecture at some other date. So let's worry about that later on in the semester. Okay, let's see. Okay, there's some contact information here. My name is Alex. You can just call me Alex. I have my phone number and email. Okay, don't call me on the phone. But you can send me an email. That's fine. My office number. My office hours are Wednesdays, 3 to 4 p.m. You can always come then. You can always stop by any other time. But if you come by some other time, I may ask you to go away and come back at a different time when I'm available. We have 2 TAs, so an embarrassment of riches. So Guillermo and Ioannis are the TAs for this semester. Their contact information is here as well. They are here to serve. They serve at your pleasure. So make use of them. Don't call them, probably. Just send them emails. Yes, so the TAs have scheduled their office hours on Fridays at 10. I believe I put the location here. All of our office hours and offices and stuff like that are up on the 3rd floor. I guess you guys scheduled a 2-hour-long thing. Okay, we'll see if you guys really need 2 hours of discussion every week. I think you're planning on running it just as an informal office hours, nothing formally arranged, but you should feel free to stop by and ask questions, seek wisdom, things like that. Okay, good. So how many of you are officially registered for this course? Most of you? Okay. Anyone who is not officially registered, please do send me an email so I can add you to the email distribution list. Because if I have to cancel class or something like that, I'll send an email out, and that way you'll get the announcement. Or if there's a typo on a problem set or something like that. So please, if you're not registered, send me an email so you'll be on the list. If you are registered, I will send you an email at your official, whatever your official McGill email address is. So either check that or have it forwarded. to one account you do check. Oh, yeah, okay. So as you can notice, I do use this tablet machine when I lecture, so you can see it sort of gets projected behind me. I use this instead of a blackboard. It's something I've been doing for a couple of years now. It works pretty well. It has advantages and disadvantages. One advantage is that I can record all of my lectures. So this lecture is currently being recorded. And so like if you go, that means you can go to the course website, which is in the syllabus, and you can download a lecture that you missed or something like that. And it also means that we have written course notes for everything that I say in class. So if you don't feel like taking notes, you don't have to. And there's even all of the lectures and recordings from last year's version of this course. I wouldn't, I think I'm probably going to change a lot relative to what I did last year because I've figured out a lot of things about how to teach this course better. So my last year lecture notes and stuff like that aren't necessarily going to be a great guide to what we're doing this year, but that's certainly a helpful resource if you want that there. Okay.
Does this record well my questions, my questions?
Yeah, it doesn't, it's not great. Like the microphone on the laptop isn't great. If you want to buy me a better microphone, you could do that, and that might help. So usually, it records the sound of my voice pretty well, but it doesn't pick up so much. I mean, if you sit in the front row, it's probably okay.
No, it's just some people might know their privacy.
Yeah.
Or does not hear
Oh,
very well.
sure. That's if you don't want your voice posted. Okay, I guess that hadn't occurred. Like if you don't want your voice to appear on I guess that hadn't occurred to me. Well, if you feel that that's a problem, please let me know, and we'll figure out I don't know. Okay, if anyone has a concern that they don't want their voice to appear on some recording on some random physics field theory course website, let me know, and then we'll discuss it, I guess. I don't know. Okay. Let's see. Anything else I have to say? Yeah, I can't guarantee that I'll record every lecture. My track record is about 1 out of every 10 times my computer doesn't work. So rely on the recorded lectures at your own risk. Let's see, grades. This is a graduate class. You're all adults or some close approximation thereof. There aren't exams. There's just problem sets. So do the problem sets, and that is what your grade will be based on. Also, how should I say this? This is a graduate class. Grades don't really matter in graduate school, so don't worry about your grade. If you work hard and learn quantum field theory, you will do well. Okay, so don't stress out about your grades. Let's see. Yeah, so there'll be problem sets. I'm not going to give a final exam. In the past, I've given take-home finals, which are like a 24-hour, basically like a glorified problem set. But you have to, but it's kind of a little more formal. What I did last semester, and which worked well, and which is what I'm going to do here, is that I'm not going to do a sort of official take-home final. Instead, what I'll do is the last problem set that I give you is going to just be a little longer and more fun, okay? And it'll be a little bit more like a project, okay, where you'll work through a big chunk of material that we don't have time to do in class. I haven't decided exactly what that'll be, but it's not going to be, it's just going to be another problem set, but it'll be a little longer and more fun. Okay, good. Let's see. Yeah, the problem sets are hard. Okay, they're long, and so don't leave them to the last minute. They're going to be due once a week. I'll hand them out on Thursdays. They'll be due the following Friday. If you turn them in late, you will lose marks. If you turn them in very late, you will lose lots of marks. Let's see. I mean, there's information here you can read. You can turn them in the mailbox in the physics, on the other side of the first floor. There's a mailbox with the name of this course on it, I believe. Yeah, if you need an extension on a problem set, that's fine. Just contact me or one of the TAs beforehand, before the problem set is due. The problem sets are due at 3:30 on Fridays, not later, because the colloquium is at 3:30. And that way you can turn in your problem set and go right to the colloquium. Let's see. Oh, yeah. Okay. You can work together. I encourage you all to work together on these problem sets. You are each other's greatest resource. It's not actually true. It's probably pretty close to true. So work together, but any work that you hand in has to be your own work and has to reflect your own understanding. Don't copy from each other. Don't copy from any solutions that you might find floating around in the world out there. That's plagiarism, and if the TAs or I suspect that someone has plagiarized, your case, we'll tell the dean, or we'll forward that to the appropriate authorities. And that unfortunately has happened in the past. Okay, so just like we're all in this to have fun. So just do your problem sets as well as you can. Don't worry. Don't go hunting around for past solutions or something like that. Good. Okay, let's talk a little about prerequisites. So this is a graduate class, which means that I'm going to assume you basically have the standard physics undergraduate curriculum under your belt. Okay, that means a full year of quantum mechanics. It means a solid course in electromagnetism, probably a full year course at the level, say, of Griffith's book. The quantum mechanics is about at the level of Sakurai's book, or I guess Griffith's book, but I prefer Sakurai's book. Mechanics, okay, classical mechanics at the level of whatever the classical mechanics book is they're using nowadays. It was Marion and Thornton a while ago. I'm not sure what it is now. Let's see, continuum. How many of you have actually seen continuum mechanics? It's never really taught anywhere. Okay, so I'm not going to assume that. But I will express my disappointment that nobody ever learns continuum mechanics. Special relativity, more or less at the level that you learn in an upper level undergraduate E&M class. So for example, how many of you took an E&M class out of the Griffiths book? Most of you. So for example, that section on special relativity in the Griffiths book is about what I'll expect. I think it's chapter 10 or 11 or something like that. Just for my information, how many of you are master students in the physics program here? Most of you. Okay. What fields are you guys in? High energy. Most of you are in high energy. Condensed matter. Okay. So how many people are in high energy theory? Okay. Nuclear theory. How many of you are in nuclear theory? Okay. How many high energy experimentalists? Great. Good. How many condensed matter theory, say? Condensed matter experiment? Any good? Any great? Any math people? Any undergraduates? We've got a couple. Okay. Are there no other undergraduates taking? Last year we had like 6 or 7 undergraduates. Okay. So only 2. That's okay. That's fine. No judgment. Okay. Let's see. Yeah. I mean, what quantum mechanics textbooks did you guys use? I'm curious. Which one? Griffiths. Did most of you use Griffiths as your undergraduate text? How many of you saw the Dirac equation in your undergrad class? Just a couple of you. Okay. We are going to be doing the Dirac equation. I'm not assuming that you've seen it. And most of you took a Griffiths as your E&M book. Okay. Good. And let's see. Okay. I'll also assume all of the usual math. Okay. Multivariable calculus, stuff like that. There is a reasonable amount of complex variables stuff in quantum field theory. So if you're a little rusty on your complex analysis, that is something you might want to brush up on. How many of you have seen the complex variables class? It's usually required, but not everywhere. It's not like it's not like you're going to be desperately missing something if you haven't seen that or don't remember all of it. But it is the sort of thing like multivariable calculus, partial differential equations, linear algebra. Complex variables is freely used in this course. And so you may have to do a little reading to remind yourselves of a few things. Okay, let me just probe your knowledge a little bit more. So in your quantum mechanics classes, how many of you saw the path integral formulation of quantum mechanics? Okay, so only about half of you. Or are you being shy? Raise your hands really high if you saw the path integral formulation of quantum mechanics. Okay, more than half of you, fine. But not many people saw the Dirac equation. How many of you feel comfortable with special relativity, say, at the level of Griffith's book? Okay. Like, how many of you, if I said the metric of Minkowski spacetime, know what that means? Okay. not everybody. Not everybody. Okay. How many of you feel could write down a Lorentz transformation? Okay. Good. How many of you know what a 4 vector is? Okay. Okay. So that gives me some sort of understanding of where you guys are sort of coming from, more or less. Let's see. Anything else I need to know? Okay. As far as textbooks go, the textbook for this course is going to be the one by Peskin and Schroeder. It's the standard textbook on quantum field theory. You know, last year I tried using a different textbook, and I ended up just coming back to Peskin and Schroeder and using that one to prepare all my lectures because it's the best. So that is the one we're going to follow. The explanations in it are really very good. And it's kind of got everything you need to know. The only problem with this textbook is that it's a bit encyclopedic. And so it actually has a lot more than you need to know. And I think for a lot of students using that textbook to learn quantum field theory, it's difficult to tell the difference between the things that you need to know and the things that you can kind of gloss over and come back to at some later time. To some extent, that's what the lectures are for. But it is useful, you know, let's put it this way. Quantum field theory is a very, very big subject. I mean, to some extent, it's a subject that's impossible to teach in just a year. So it's a very big subject. And, you know, a textbook like Peskin and Schroeder has far more material than you could really cover in a year. The other thing that I'll mention about quantum field theory is that it's a new subject. You know, the foundations of quantum field theory really were only laid in the 40s, 50s. The standard model of particle physics was only completed in the 70s, really. And so it's a new subject, which means that there has not been enough time for a single kind of coherent pedagogical structure of quantum field theory to emerge. You know, we as a species have had several hundred years of practice teaching classical mechanics and over 100 years of practice teaching electromagnetism, okay? So there's been a chance, so there's a very well-oiled curriculum for courses like that. Quantum field theory is not nearly as well organized and frankly well understood a subject, okay? And I think because of that, there is a huge variety of textbooks out there, all of which are really quite different from one another. I mean, it's possible to take a quantum field theory course taught by a particle physicist, and a quantum field theory course taught by a mathematician, and a quantum field theory course taught by a condensed matter theorist, and there's not going to be a single bit of overlap between those three courses, practically speaking. I mean, because there's many, many different ways of approaching the subject, and there's many, many different sorts of points of view that one can take. And so what I've done here is I've selected a bunch of different textbooks that I think sort of reflect somewhat different points of view. So what I would do is I would recommend that you pick up a copy of Peskin and Schroeder. And I would also recommend that you look seriously at the two other texts that I listed as alternate texts. So these are both somewhat more recent than the one by Peskin and Schroeder. The book by Tony Z is like one of my favorite physics books of all time. It's very informal. It's very conceptual. It contains very few sort of practical computations, but it's packed full of intuition. It's like, I call it bedtime reading for physicists. I mean, it's very different from almost any other physics textbook you'll read. And even though it's written in this very informal style, it actually has a lot of very, very deep insights on a lot of material that you just don't see anywhere else, that I've never seen in a textbook before. So I think that, you know, spiritually, the book by Z is probably, you know, the book that I use in my head when I think about how I want to teach this course. But it doesn't really teach you to do any calculations, so it's not really appropriate as a main textbook for the course. But still, it's something that I'd encourage you to take a look at if you have the chance. It also is nice because it has a lot of condensed matter physics in it. Quantum field theory is often, you know, it's considered, you know, quantum field theory is a subject that is primarily used by particle physicists, and indeed, to some extent, quantum field theory is particle physics, and particle physics is quantum field theory. But quantum field theory also includes a lot of tools that are very useful in many, many other areas of physics, particularly condensed matter theory. Okay? And so one of the things that I'm going to be trying to do as I teach this course is include lots of applications to condensed matter physics and materials physics. Not just because these are important things that you need to learn, but also because I think they're very important for helping you develop your intuition for thinking about quantum field theory. And so this book by Z is really great. It's got a lot of really nice condensed matter applications. The book by Srednicki is also pretty good. One of the things, it's in some ways the exact opposite of the book by Z. It's very straightforward. It does tons of calculations, tons of derivations, step by step, every little detail included. It's free. You can go to the author's website and download a version of the book for free. And so it's good. Yeah, you should take a look. I mean, I think I also considered using that as a main textbook for the course, but I do think I like a lot of the explanations in Peskin and Schroeder the best. And then I've included a bunch of other different books that you can take a look at under supplementary reading. I've roughly organized them in the order from sort of most elementary to most advanced. So for example, David Tong has some online lecture notes. There's a link to them posted on the course webpage. They're really good. They're pretty basic. They're about what we'll do, say, in the first half of the first semester, something like that. But they're good. Ryder's book is a classic. It's really good. It's basically the first semester's worth of material in this class. And then there's several others that are worth mentioning. Schwartz is also very good. I used it as a textbook last year. I didn't love it, but some of the students really seem to like it. It has a lot of very different sorts of derivations from the ones you'll see in Peskin and Schroeder. So his derivation of Feynman diagrams is quite different, for example. And he has a lot of stuff. I misspelled material. Sorry about that. He has a lot of stuff on sort of the standard model and particle physics phenomenology you won't see anywhere else. Other books that are worth mentioning, the book by Zen Justin is pretty interesting. This is one of these cases where you could read this book and it bears almost no resemblance to the, some of the other textbooks because it's very, very focused on, condensed matter aspects of quantum field theory. It's a great resource. It's incredibly detailed. It's more of an encyclopedia than a textbook. But what it presents incredibly well. So it's worth taking a look at. Okay, so let's see. Maybe I'll just make a couple remarks about the content of this course and the outline. Yeah, so I'm going to try and follow the textbook Peskin and Schroeder as closely as I can. I will end up just presenting things in very different ways sometimes, in ways that are complementary to the ways that Peskin presents them. But I'll try and keep as close to the outline of that book as possible. There are a few decisions that he makes about how to present things that I think, I'm not going to follow because I'm going to try and do things in a bit more of a streamlined way. But by and large, I'm going to try and follow that textbook. Good. Yeah. Okay. I'll try and do a little more condensed matter than one would usually see in a quantum field theory course. Okay. So basically, what I'm going to be doing in this class is contained in the first part of the Peskin and Schroeder book. So the goal of this class, the first semester, is we're going to understand the quantization of scalar field theory. Well, first we'll understand what field theory is and why we need it. We'll understand scalar field theory. We'll talk about the path integral formulation of quantum mechanics and quantum field theory. We'll talk about Feynman diagrams. How many of you have seen Feynman diagrams before, actually? Okay, where did you see them? Did you see them in the undergrad, in like a particle physics kind of class? Okay. Like a sort of Griffith, the one out of the Griffiths book or something like that? How many of you have taken like a Griffiths level particle physics class? A fair number of you. Not, okay, some of you. Okay, yeah. I never quite understand, okay, I'm not going to editorialize. Okay. Yeah, so we'll talk about Feynman diagrams, perturbative methods in quantum field theory, path integrals, and then we're going to move on to discuss spinors, the Dirac equation. How many of you know what a spinor is? You should sort of know what a spinor is from quantum mechanics. Nobody actually knows what a spinner is the first time they see it. I mean, how many of you saw spinners in your, okay, I can't even ask. If you didn't see spinners in your quantum mechanics class, don't tell me. Okay. But you'll learn more about them here. Good.
But first semester, you mean like you're referring to the second semester of HOT2, right?
That's right. So this is a 2-semester long course. This is Quantum Field Theory 1. Next semester is Quantum Field Theory 2, 673.
Yeah.
Yes.
Not everybody takes the
What's that?
part, right?
What's that?
So not everybody takes it.
Not everybody takes the second part, but you should. There's a lot of good stuff there. Okay. I mean, so I'll tell you, roughly speaking, what's going to be in the first semester as opposed to the second semester. Right. So this semester we're doing the Dirac equation, fermions. Then we'll talk about quantum electrodynamics. We'll talk a little bit about the Higgs mechanism and superconductivity. And finally, we'll end up with quantum electrodynamics. Okay. So the goal sort of in this course is to introduce quantum electrodynamics, and sort of the end goal, that the holy grail at the end in December, or hopefully November, is that we'll have an understanding of quantum electrodynamics and the ability to compute sort of basic scattering processes in quantum electrodynamics. And along the way, we'll learn all sorts of interesting features of quantum field theories, applications to condensed matter physics, applications to quantum electromagnetism, a little bit of classical field theory, solitons, solitons and stuff like that. The second part of this class is where things actually get quite interesting. Okay, the first part is pretty interesting, but the second part is even more interesting. So beginning in around January, we'll do renormalization and the renormalization group flow. By the way, how many people have seen renormalization, say, in a StatMech class? So you did like block spin renormalization or something like that?
And epsilon expansion.
You did the epsilon expansion. Okay. So often one sees that in a sort of StatMech class. So we're going to really do that from a quantum field theory perspective. Okay? So there'll be renormalization and renormalization group flow in the beginning of the second semester before moving on to the standard model of particle physics. Okay? And so by the end of the year, you will know what every particle in the standard model means, how it interacts with all other particles, and at least in principle, how you could compute just about anything you like. Okay. Well, that's not actually true at all. How you could compute lots of things. Good. Yeah. I mean, I will say that in teaching a course like this that's divided into 2 semesters, you really have a choice. Like, you can either do spinors and quantum electrodynamics in 1 semester, or you can do renormalization in 1 semester. You really can't fit them both into 1 semester. I tried, but you really can't. So I've made the choice, which I think is the sort of standard one, that what we're going to do is this semester is going to focus largely on what are called tree-level processes, leading order processes, where a lot of the subtleties of Feynman diagrams and renormalization are not too important. And this will allow us to quickly understand quantum electrodynamics and all sorts of features thereof. And it's only next semester that we'll get into the nitty-gritty details of renormalization and stuff like that. And that is a subject that is very, very deep, very, very important, but kind of hard to wrap your head around the first time you see it. And so it's something that we'll need to spend a fair bit of time on. Okay, are there any questions or comments before we get going? Any thoughts? Good. How many people think they will take the second semester, just for my information? Not a ton of people, some more. Okay. Half a dozen people. No one from this side of the room? What's that? The experimentalists. We had some experimentalists last year who took the whole thing. How else are you going to know what a gauge boson is? How else are you going to know what a gluon is? Okay, I'm not going to, yeah. So, the second semester is really where we do things like QCD, non-abelian gauge theory, the particle content of the standard model, spontaneous symmetry breaking, stuff like that, the Higgs mechanism. I mean, in this semester, we'll be able to do the Higgs mechanism and electromagnetism, otherwise known as the theory of superconductivity. Okay. It's only next semester when we talk about non-abelian gauge theory that we'll really get into, you know, the sort of nitty-gritty of the Higgs mechanism as it applies to the Standard Model. Good. Any questions, comments? Everyone happy? As happy as you can be? Okay, good. So let me just begin, rather than starting out with any real technical details, let me just begin with the remainder of this class today, talking a little bit about what quantum field theory is and why we need it. Okay. So the quantum mechanics that you have seen so far in your lives is really the quantum mechanics of a single particle. So in the quantum mechanics that you've seen, you are typically focusing on systems with only a single particle that could be neither created nor destroyed. So you might study a particle in a box or a particle in a potential, or if you were studying the hydrogen atom, for example, you would study a single electron moving in the Coulomb potential of the nucleus of a hydrogen atom. And quantum field theory is the generalization of single particle quantum mechanics to systems where particles can be created or destroyed. So what does that mean? That means that we're studying systems where you don't necessarily just have one particle. So let's say a Hilbert space describing the states of one particle. You don't have a gigantic Hilbert space where you have some states which have no particles, some states with one particle, some states with two particles, and so forth. And you have various processes that can either create or destroy these particles. So, you know, when we talk about quantum field theory, as compared to single particle quantum mechanics, there's both good news and bad news. Okay. So the good news is that the basic structure of quantum field theory is the same as in quantum mechanics. So what do I mean by this? What I mean is that the basic sort of formal description of the space of states and the kinematics of quantum field theory are really the same sorts of things that you've already learned in your quantum mechanics classes. So, for example, the state of a system in quantum field theory is described by some sort of ray in a Hilbert space, just as in quantum mechanics. By the way, when I say ray in a Hilbert space, do you guys know what I mean, as opposed to a state in a Hilbert space? Okay. Raise your hand if you know what that means. Okay, good. So another way of saying that is that states in quantum mechanics live in a Hilbert space, and states in quantum field theory live in a Hilbert space. Okay. When I say a ray in a Hilbert space, I'm just reminding you of the fact that when you describe the physical state of a system in terms of a state in a Hilbert space, if you multiply that state by an overall phase, the state vector by an overall phase, it doesn't change the actual physical state that you're thinking about. You know, if you think about, say, a two-state system, you take the wave function, you multiply it by I, multiplying it by a phase doesn't really do anything. So when you think about quantum mechanics, you think about a state vector, but you're allowed to multiply it by an overall coefficient, and that doesn't change the physical state of the system. Okay. But the important point is that in quantum field theory, the states are described by elements of a Hilbert space with all of the sorts of properties that we expect of Hilbert spaces. You can add two states together to get another state. You can multiply them by complex constants to get another state. There is an inner product, that is to say there is a norm on this Hilbert space, and so on and so forth. These are features we'll be discussing in more detail. By the way, just for my education, since most of you are master's students, how many of you are taking 551 or something like that? Like the graduate level, the master's level quantum mechanics class? And how many of you have already taken it or something at that level? Okay. If you're not familiar with some of the basic, you know, it's not a bad class to think about taking. Okay. Good. Okay. So states live in a Hilbert space in a quantum field theory, just as they do in quantum mechanics. Observables, that is to say the quantities that one measures in experiments, are given by Hermitian operators acting on this Hilbert space, just as in quantum mechanics the position operator is realized as some Hermitian operator acting on this Hilbert space. And time evolution is given by a unitary operator on the Hilbert space as well. In particular, the unitary operator that generates time translations is e to the I ht over h bar, where h is a Hamiltonian, just as it is in normal quantum mechanics. In principle, if I wanted to describe quantum field theory, I could give you some space of states, and we could talk about a wave function that's just like the Schrodinger wave function. That's a function of this space of states. I could give you a Hamiltonian, just like the Hamiltonian in single particle quantum mechanics, and one could go ahead and just compute this. Okay? Now, typically in quantum field theory, we don't talk about wave functions and Schrodinger equations in the same language that we do in quantum mechanics, but it's important to remember that the basic sort of mathematical structure, the basic formal structure of quantum field theory really is the same as it is in quantum mechanics. So there's no need to complete, when you learn quantum mechanics, you need to fundamentally sort of, scoop out the insides of your brain that learned classical physics and replace them with some new parts of your brain that understand quantum mechanics. You don't need to do that in quantum field theory. The basic conceptual structure is the same. Okay? But there is, of course, bad news, which is that although the conceptual structure of quantum field theory is the same as in quantum mechanics, it is technically much more complicated. In fact, even classical field theories are rather complicated. When you think about a typical simple classical dynamical system like the harmonic oscillator, this is nearly trivial. It's exactly solvable. Once you sort of learn classical mechanics, there's just not too much to say about the harmonic oscillator. But even classical field theory, there are entire courses, many of which you've taken, devoted to the subject of classical field theory. Electromagnetism is a year-long class. That's a classical field theory. It's not just a classical field theory, it's practically the simplest classical field theory you could write down. Okay. In particular, it's one where there are no interactions, in the sense that photons don't carry charge, and so they don't interact with each other. You can shine a flashlight here in one direction and another flashlight in a perpendicular direction, and the photons don't bounce off of each other. So that's what we mean when we say that electromagnetism is a free classical field theory. An example of a not free classical field theory would be the theory of general relativity. If you had a flashlight that could shine a beam of gravitons, and you shined one this way and you shined one that way, they would bounce off of each other. Okay? And even classical general relativity is an incredibly complicated and rich subject, which is really not completely understood. Okay? So because even classical field theories can be incredibly complicated, it shouldn't surprise you that quantum field theories can be incredibly complicated as well. And unfortunately, what this means is that there are very few exact computations that are possible. In your quantum mechanics class, every week on a problem set you do some sort of exact calculation where someone hands you a Hamiltonian and a potential and you calculate the spectrum and blah, blah, blah. Life is not nearly so simple in the real world. And in quantum field theory, there are really very, very few examples of systems where you could do something like compute the exact spectrum of the theory, precisely without any approximations. And so because of that, a lot of what one does in quantum field theory is focus on various perturbative methods. So most famously, of course, we have the method of Feynman diagrams, which is just, in a sense, a perturbative method for computing, say, path integrals or correlation functions or observables in these quantum mechanical systems. But there are other sorts of approximation methods as well that one can develop, some based on normalization, some based on other sort of features of quantum field theory. And to some extent, a lot of the technical details of this course and what makes it difficult involves the development of these perturbation methods. Okay. So let me just sort of pause here and see if there are any questions. Also, by the way, I really want to encourage all of you to ask questions. You know, I'm going to be very disappointed if nobody asks any questions right now. So please feel free to interrupt me and ask questions. Any questions? Okay, maybe I didn't really say very much, so maybe there's nothing to ask. Sure, go ahead. No need to raise your hand. Well, I guess you could raise your hand.
Questions just for the sake of asking questions,
Mhm.
but my mind is blank.
Oh, okay, fine. Well, did you have a question?
No.
No. Okay. Well, I'll continue and someone will come up with a question. Good. Okay. So in a quantum field theory, it's just a quantum mechanics system, except it's a quantum mechanics system where we're allowed to create and destroy particles. Okay. And before I proceed, maybe I should just say precisely what I mean by a particle. What I mean by a particle is, loosely speaking, any sort of localized excitation, a degree of freedom of a system associated with a particular location in space and time. So there are all sorts of particles that we could try and study. So for example, we could study elementary particles. You know, in the standard model, things like an electron or a quark might be an elementary particle. Or we could study particles that are some sort of complicated bound states of elementary particles. A proton and a neutron, for example, are all bound states of elementary particles as far as we understand. Or, and more generally, we could mean any sort of localized excitation that emerges from some sort of complicated dynamics. Okay. So, for example, if you're studying a material, let's say we're studying some sort of crystal, you have atoms on a lattice, and then you look at some localized excitation of this lattice that gives you some sort of propagating wave solution. So this would be known as a phonon. If you've seen, for example, the Debye model of solids in your statistical mechanics class, that's a classical field theory, essentially. That is a model for the phonons, which are these essentially propagating sound waves or propagating perturbations of some sort of crystal lattice. Okay. Or if you're studying a superconductor, in a superconductor, that's a system where the electrons obey, because of the complicated dynamics of the system, obey some sort of complicated interactions that cause them to form bound states that are known as Cooper pairs. And the dynamics, in fact, even in some cases, the classical dynamics of these bound states is what leads to superconductivity. And of course, in the world of condensed matter physics, there are all sorts of very complicated systems that can be thought of in terms of some sort of emergent particle dynamics or some sort of emergent degrees of freedom. And we'll be encountering many of these as we go on with this course. And of course, the distinctions between these three different types of particle excitations that I've listed here are in some sense completely artificial. Okay? So for example, a Cooper pair is a bound state. And in fact, if you'd asked particle physicists 50 years ago, whether protons and neutrons were fundamental particles or whether they were bound states of something else more elementary, they might have thought that they were elementary particles. And we only now realize that they are, in fact, bound states of more fundamental particles. Similarly, there are many theories that postulate that what we regard as the elementary particles are, in fact, some sort of low energy effective excitations that arise from some sort of more fundamental dynamics. Okay? So for example, there's a lot of kerfluffle nowadays about the idea that gravity, the graviton, which of course is right now, which is usually viewed as an elementary particle, in fact is some sort of emergent dynamics from some more complex underlying elementary description. Okay. So this is what we mean by a particle. I'm not, at least at this point, going to be terribly precise about exactly what I mean by a localized excitation. So we'll try and be a little bit more precise starting next class. But for the time being, you can just view a particle as any sort of localized excitation. Any questions? Good. Okay, so far I've just talked about a particle as some sort of localized excitation. But it turns out that, so one might imagine that it's perfectly possible to study your favorite theory. You know, it's perfectly possible to study all sorts of interesting theories where you don't have to include the effects of, we don't have to include dynamics where particles can be created or destroyed. But in fact, it turns out that special relativity is intimately related to the ability to create and destroy particles. Okay. In particular, it turns out that if we try to include the effects of special relativity in quantum mechanics, one is inevitably forced to consider processes where particles can be created and destroyed. And so, for example, you must consider things like multi-particle states. And that's actually a rather surprising statement. Okay. So, for example, previously in your lives as physicists, when you were studying single particle quantum mechanics, okay, you had, say, a particle, say the hydrogen atom, okay? And you had an electron and the dynamics of the electron as it orbits the nucleus of the hydrogen atom. And you studied the classical Coulomb potential using non-relativistic Newtonian dynamics. So the Hamiltonian of the electron moving around the nucleus of the hydrogen atom was just that given by Newtonian dynamics. But you might think like, well, you could just include the effects of special relativity by modifying the Hamiltonian of an electron. And then you would have a perfectly good and well-defined theory of a relativistic electron, the relativistic hydrogen atom, a relativistic electron moving in the presence of a nucleus. Okay? But it turns out that you can't consistently do such a thing. Okay? And because of that, special relativity, people often view quantum field theory as the theory that arises when we try and unify special relativity with quantum mechanics. And so that's what I'd like to try and describe to you now. So the first comment that I'll make is just a very rough comment, which is that, so let's imagine that we're trying to study a relativistic hydrogen atom. Okay. So in a relativistic hydrogen atom, you could imagine computing the corrections, say, to the spectrum of the hydrogen atom due to special relativity. And you could also, and the question is, and so such corrections will be important when the energy of the electron is of order mc squared. Why do I say that? Well, just as an order of magnitude estimate, the energy of an electron that's moving around a hydrogen atom is 1/2 mv squared. That's its kinetic energy. And the corrections due to special relativity will be important when the velocity is of order the speed of light, say, times some number of order 1. Okay. That means that the typical energy scales where you would need to worry about the effects of special relativity in the hydrogen atom are when you're talking about electrons that have energy that's of order mc squared. Okay? But, of course, you know what mc squared is. Mc squared is the rest energy of an electron in special relativity. E equals mc squared. So E equals mc squared is the threshold for the production of new particles. So if you consider an electron with energy of order mc squared, then you're studying energies where it's possible to, at least energetically, for an electron to spontaneously appear out of the vacuum. So let's just try and make that argument a little bit more precise. So let's imagine that we're studying the hydrogen atom again. And let's investigate what the corrections to non-relativistic quantum mechanics look like due to special relativity effects. And what we'll conclude, and I'll go through this argument for you in a second, is that the corrections to non-relativistic quantum mechanics due to special relativity are the same order as those due to multiparticle states in a theory where we allow there to be 1 electron state, 2 electron state, 3 electron state, and so forth. So how do we see that? Well, let me just remind you of the expression for energy in special relativity. Okay. So the rest energy of an electron in special relativity is the square root of m squared c to the 4th plus p squared c squared. Okay. So that's the formula for energy in special relativity. When the momentum of the electron is equal to 0, that is just equal to mc squared. That's the usual E equals mc squared rest energy of a particle. And if you imagine Taylor expanding that square root order by order in powers of p, the first correction to this will be of order p squared. What will it be? Let's see, it'll be p squared over 2m, just expanding out the first non-trivial term in powers of p. So what is that? That's the usual non-relativistic kinetic energy of a particle with mass m. And then the next term will be, let's see, p to the 4th. Then it's over m cubed c squared plus dot dot dot. Okay. I'm only going to do an order of magnitude estimate here, so I'm not going to pay too much attention to the factors of order 1. So what does this mean? This means that if you want to calculate the corrections to the energy levels of an electron due just to special relativity effects, then delta E over E, so the typical size of a correction to the energy level is found by taking the ratio of this term here, so that term there. What is that? Well, let's see. That's p squared over mc squared, otherwise known as v squared over c squared. So if you have a particle moving with velocity v, then the typical correction to the typical size of the correction to the energy due to special relativity is of order v squared over c squared. Okay, but what is the typical correction due to multiparticle states? In particular, we're imagining this electron, say, moving around the hydrogen atom, and we're imagining that in addition to the single electron state, there's also a 2 electron state, a 3 electron state, a 4 electron state, and stuff like that. And all of these states, these multi-particle states, will have energies that are of order mc squared. Okay. maybe 2 mc squared for a 2 electron state, 4 mc squared for a 4 electron state, and so on and so forth. And then you can ask, what are the sizes of the corrections due to these multi-particle states in the spectrum of the single electron system? So how would you go about computing that? Well, to compute that, you need to imagine that there's some sort of interaction between the single particle states and the multi-particle states. Okay? So let's just understand what this looks like very generally. So let's imagine that you have the Hamiltonian describing the single electron system, and then you add in some sort of perturbation that describes the interaction between the single particle states and the multi-particle states. And then perhaps you remember the formula for the corrections to energy levels using perturbation theory using time-independent perturbation theory in quantum mechanics. So that says that the correction to some energy level due to a perturbation in the Hamiltonian, so I'm just going to write down the formula to the correction for the ground state energy, just so you can see how that looks. That's the expectation value of the perturbation term plus the first subleading correction is the probability that your perturbation pops you into a new state that I've called n, divided by the energy of your initial state and the energy of the new state. Okay. So it's the second term that I want you to pay attention to here. So this says that if you have, so let's say I'm studying my single particle electron system, and you imagine that there's some interaction in the Hamiltonian between this system and the multi-particle states. This is telling you that there are going to be corrections to the spectrum of the single particle hydrogen atom that are proportional to 1 over the energy of whatever new states you're adding. So 1 over the energy of these multi-particle states. So what does that mean? That means that if you want to calculate the change in the energy levels of an electron in the hydrogen atom due to the 2 electron states, 3 electron states, and so forth, that should be proportional to 1 over the energy of these multi-particle states. But this quantity that I'm writing down here, delta E over E, is dimensionless. So the numerator should be the energy of some sort of typical system, some typical state that you're studying, over the energy of the multi-particle states. So if you consider a process where the energies are, where you have an electron moving at velocity v, this will be 1/2 mv squared over the energy of the new multi-particle states. And so this is also of order v squared over c squared. Okay. So what does this teach us? What this teaches us is that if we consider special relativity effects as corrections to standard non-relativistic quantum mechanics, then we should also allow for processes that create or destroy particles. In the example of the hydrogen atom, that means you would have to allow for processes where the single electron could, so what would this term here describe? This would describe some sort of physical process where a single electron undergoes some interaction and maybe it becomes a 2-electron system. Well, okay, because of charge conjugation, it would have to be 2 electrons and a positron, and then it undergoes some other interaction and then goes back to being an electron again. And what this sort of back-of-the-envelope analysis is telling us is that any corrections to the hydrogen atom due to special relativity kinematics, just the formula for energy in special relativity, are going to be of order the same size as those due to multi-particle states. So this is why really the inclusion of special relativity in quantum mechanics tells us that it's truly necessary to consider the creation and the destruction of particles. Now, this is not to say, of course, that all quantum field theories necessarily involve special relativity. Okay. We've seen that special relativity implies that you have to include particle creation and destruction. But, of course, there are also theories that have particle creation and destruction that don't have special relativity. So, for example, if you consider just about any material, any condensed matter system, those are like something with phonons or Cooper pairs or something like that. These are non-relativistic systems, okay, because, by and large, most of the materials in laboratories that we're studying are moving at speeds far, far slower than the speed of light, okay, so you don't really need special relativity to describe them. But these are still quantum field theories nonetheless. So although some people, sometimes people think that quantum field theory is something that you only need to study if you're including the effects of special relativity. That is not true, and that's something that I do want to emphasize. It is, however, true that if you do consider the effects of special relativity in quantum mechanics, then you must consider quantum field theory. In fact, the argument that I've presented here is an argument that the typical corrections due to particle creation and destruction are the same size as the corrections due to special relativity. But in fact, you can take this one step further, and this is something that I'd like to describe in the last few minutes of class today, because I think it's a very important point, which is that it turns out that it's impossible to construct a consistent single particle quantum mechanics theory which is consistent with special relativity. Okay. Maybe I should put a little caveat there and say that it's a spinless theory, because Dirac constructed very cleverly a theory of quantum mechanics consistent, something that was in a sense a single particle theory of quantum mechanics, consistent with special relativity for particles with spin 1/2. Of course, those of you who studied the Dirac equation will know that it's actually secretly a multi-particle theory as well. That's something that we'll come back to later on in this class. But the basic point that I want to make is that, and this is something that I'll just go through in the last few minutes of class, is that it's impossible, in fact, to have a consistent theory just of a single particle in quantum mechanics moving relativistically. So to see why that is, let me pause actually and see if there are any questions. Okay, to see why that is, let's just consider Schrödinger's equation. So Schrödinger's equation tells us how wave functions evolve. Okay. They evolve according to a Hamiltonian. And to make this relativistic, let us just, instead of taking the Hamiltonian of a free particle in non-relativistic quantum mechanics, let's just replace that by the Hamiltonian that you would get if instead of using the non-relativistic kinetic energy of a particle for the Hamiltonian, we use the relativistic kinetic energy. So in particular, what we're going to study is the Schrödinger equation, where your wave function obeys a relativistic version of Schrodinger's equation, where we now have this relativistic Hamiltonian. And here, as usual in quantum mechanics, P is the momentum operator, which is minus IH bar times the spatial derivative. Everyone with me so far? Okay, it's clear what we're doing. Just considering the natural generalization of Schrodinger's equation describing a single particle, but now the energy is the relativistic expression for the energy instead of the non-relativistic one. Don't worry, we're not going to study this theory for very long, because we're quickly going to discover there's some deeply, deeply wrong, deeply sick features of this theory. So let me just, to show that to you, do a quick calculation. This calculation is not particularly important per se to things that we're going to be doing later on in this course, but it does demonstrate, let's say, some of the techniques and tricks that we'll be using for a lot of calculations later on in this course. Okay. So it's probably a good chance for us to start getting used to these sorts of things. So the first thing that I'm going to do is I'm going to set h bar and the speed of light equal to 1. Okay. These are so-called God-given units. Okay, I don't actually like that phrase very much, but that's what people sometimes call it. What does this mean? This means that h bar has units of action, which is energy times time. C has units of velocity, which is length over time. So this just means that I measure, say, lengths in units of time, so distances in light seconds or something like that, and that I measure energy in units of 1 over time, since h bar has units of energy times time. So maybe what I'll do on the next problem set is you'll get some exercises making sure that you're fluent in these God-given units. I hate that phrase. Okay, but we'll never get anywhere if we keep our factors of h bar and c in the game. I'll only include h bar and c in this course occasionally for dramatic effect, but generally speaking, they'll be set equal to 1. Okay, so the Hamiltonian is a function only of the momentum. So what I'd like to do is use momentum eigenstates, just as I would if I were studying a free particle in non-relativistic quantum mechanics. Okay. So what does that mean? I want to expand in a basis of states that are labeled by their momentum. So I'll call the momentum k. And the momentum eigenstate k has the property that it's an eigenvalue of the momentum operator p with eigenvalue k. K is some 3 vector. So, for example, the wave function of the momentum eigenstate k is going to be e to the ikx times some sort of normalization factor to make it appropriately normalized, which is the sort of thing I often forget and which won't be too important for this calculation. So these are the usual plane waves that are the solutions of the free particle in non-relativistic quantum mechanics. And they're also the eigenstates of the Hamiltonian in relativistic quantum mechanics. Okay? And the eigenvalue, so of one of these momentum eigenstates, is just equal to what I'll call omega, which is the square root of m squared plus k squared. Okay? Remember, I'm using units where c is equal to 1. Okay, so those are so we've solved the time-independent Schrodinger equation. The eigenstates are the usual plane wave eigenstates, and their energies are just given by these omegas that I've written here. Okay. So far, everything looks hunky-dory. Okay, but let's start trying to compute some observable in this theory. And let's ask the following question, which I think is the sort of basic question that one might ask in a single particle quantum mechanics theory, which is, what is the amplitude for a particle to move a given distance in a given time? So let's say for a particle to travel from, say, the origin, x equals 0, at time t equals 0, to a position x at time t. So how would we go about computing that in this theory? Well, just remember in quantum mechanics, e to the iht is the time evolution operator. So you would start with a position eigenstate at the origin, apply the time evolution operator, e to the iht, and then compute its overlap with some position eigenstate at later time. So how would we go about computing this thing? Well, the Hamiltonian is diagonal in momentum space, but not in position space, okay? Just like it is in non-relativistic quantum mechanics of a free particle. So the easiest way to do this is to insert a complete basis of states. Okay? If you never learned this trick in your quantum mechanics class, now is the time to learn it. We're using, my favorite trick in quantum mechanics is to use the fact that 1 is equal to the integral d3k times k, right? So this is the statement that the momentum eigenstates form a complete basis. Okay? So you can insert a complete set of momentum eigenstates, and this is the integral d3k times the overlap between x and one of our basis states k times k e to the minus iht acting on the state x equals to 0. Everyone with me so far? Okay. So we can now use the fact that we know what that is. That's just the wave function, the momentum eigenstate wave function. Okay. And of course, this guy. So this state is an eigenfunction of h. So we can take that this operator e to the minus iht and act it on k from the right. And what do you get? You find that this amplitude is the integral d3k times e to the I k dot x minus I omega kt. So that's just some straightforward integral. You could do it. The answer is sort of complicated, so I'm just going to mention a couple of its features. So in order to understand this answer in a little bit more detail, let's just choose x to be equal to r times z hat, so that we're looking at a particle that travels a distance r from the origin to a point a distance r away in the z direction. And then let's call the absolute value of the vector k without a vector symbol. And then I'll let theta be the angle of the k vector off of the z-axis. Okay. So this is the z-axis, and there's the k vector, and there's the angle theta. So then you can just go ahead and compute this integral. So you get an integral from 0 to infinity k squared dk, right? That's just the usual Jacobian factor. And then you get a theta integral, so an integral from 0 to pi d theta sine theta. And then you get a phi integral, where phi is the angle, so it would be that angle there. An integral from 0 to 2 pi d phi. And then what was the integrand? The integrand was I times k dot x, so that's k times r times cosine theta minus omega k times t. Okay. Any questions? Everyone with me? Okay, so let's just do that integral. So I'm not going to care about the overall constant, so we can just forget about that phi integral. That theta integral is pretty easy to do once we remember that this is the same as the integral of minus 1 to 1 d cosine theta. Okay? And so we have a cosine theta there, so you just have an exponential integral that we can do. When you do the integral d cosine theta, it brings down a factor of ikr. So the integral of e to the ikr cosine theta is some number times 1 over ikr. So you get a 1 over ir, an integral from 0 to infinity, k dk. Oh, I'm forgetting about the theta integral. And what do you get? You get the exponential of I times kr minus omega kt, which I'll just write out explicitly, was k squared plus m squared times t. Good. Okay. This is the amplitude for a particle to travel a distance r in a time t. Or if I want to write this a little bit more simply, oh, sorry, I skipped a step. I skipped a step here. Let me write this. Sorry about that. I skipped a step here. So we had an integral from 0 to infinity e to the ikr, and then we have two terms coming from the two boundaries of integration here. So we get an e to the, sorry about that. We have an e to the minus I omega kt, and then we get the an e to the ikr minus e to the minus ikr, right? That comes, so one of them comes from this boundary of integration, the other comes from this boundary of integration. And so then I can write that slightly differently by just taking the second term and doing a change of variables where I take k to minus k, and using the fact that omega k is independent of k to minus k, and that this term here, k dk, is independent of the change of variables where I take k to minus k, and write this as the integral from minus infinity to infinity, k dk of e to the ikr minus I square root of k squared plus m squared times t. Okay, good. Any questions on that? I went through that a little bit quickly, but hopefully it's all more or less clear. Any questions? Maybe I can pause and see if there's a question. Good. No, is this clear more or less? Okay, so this is the integral we want to do. I don't actually want to do the integral. I just want to convince you that it's not 0 and that there's no funny cancellations here. And I'm going to describe this integral using a particular trick, which I like because it's the sort of trick that we're going to be using a lot in this course. Okay? So what I want to do is I want to think about this integral as a contour integral in the complex k-plane. Okay? So what I'm going to do is I'm going to take r greater than t, or remembering that we're using units where the speed of light is equal to 1, r is bigger than ct, where c is the speed of light. And then I want to think about this as a contour integral in the complex k-plane. And as a contour integral in the complex k-plane, what should we notice about this integrand? Well, I want you to notice that it has a branch cut. Okay? It's got a branch point at k is equal to im, which is right there. So this is the imaginary k-axis. And at points above there, you have an order 2 branch cut because of that square root. So we have, this is the branch point, and then you have a square root. And the other thing you want to notice is that the integral converges And in fact, it vanishes when the absolute value of k is large with a positive imaginary part. Okay. That's just because if you have that factor of I there, so if k is very large, is some number with very large magnitude and positive imaginary part, so let's say that you're out here, then that integrand is 0. So that means that if you want to do the integration along the real k-axis, which is what we're instructed to, you can freely deform the contour into the upper part of the imaginary k-plane. And if you deform the contour integral until it's all the way up there, the integrand is going to be basically 0. And the only thing you need to worry about is that branch cut. And so the way that you do the integral is you imagine deforming all the way up here, and then you get a contribution when you cross that branch cut. How do you calculate that contribution? Well, you really just imagine that you want to avoid crossing the branch cut, and so you end up doing an integral on a contour like that. So that the amplitude, what is it? Well, so we just end up with an integral along that branch cut. Okay. So let's let k be iz, where z is just some number that runs, so z runs from m to infinity along the branch cut. And then the amplitude is 1 over ir times the integral of z from m to infinity, z dz. And then we just, well, k was iz, so this is e to the minus zr. And then you just have to, you get contributions from either side of the branch cut. So there's one contribution from here and another contribution from there. So you get e to the square root of z squared minus m squared t minus e to the minus square root of z squared minus m squared t, otherwise known as sinh square root of z squared minus m squared t. Okay, so this is a nice expression. You could study it if you like. You could manipulate it. You could compute it numerically, even analytically. I believe it's a Bessel function of some sort. But the important point is that it's the integral of a positive definite real number. So this integral is non-zero. So what does this mean? Remember, I was assuming that r was bigger than ct. So this means that there is a non-zero probability for our particle to travel faster than the speed of light. We've just calculated the probability, or the amplitude, for our single particle quantum system with the relativistic Hamiltonian to move a distance r in a time t. And that we found that we had an answer that was very, very small because you've got this e to the minus zr here. Okay, so it's saying that it's, you're going to get an answer that looks like e to the minus mr. Okay, so if the mass of the particle is big, or if the radius is big, it's going to be a very, very small probability. But it still means that if there was a system that had only single particle states, no particle creation or destruction, just a single particle state consistent with special relativity, then you could travel faster than the speed of light. And as you may remember from your special relativity courses, going faster than the speed of light is the same as going backwards in time. A process where an object travels faster than the speed of light in one reference frame. In another reference frame looks like an object going backwards in time. I.e., you can go backwards in time and kill your grandfather. Or grandmother, because this is a grandparent, I should say. So this is bad. Theories of physics where you can go back in time and kill your grandparents are bad. They're acausal. It's impossible to say that events happen either before or after one another. And what we conclude is that any theory of single particle quantum mechanics consistent with special relativity, where you're not allowed to create or destroy particles, violates causality. So this is why quantum field theory and the process of particle creation and destruction is really an absolutely necessary consequence of quantum field theory. So that's where I wanted to stop today. Sorry, I went over time by a few minutes. I apologize. I'll try not to do that in the future. I will, but I'll try not to. Maybe I'll just make one word about, so hopefully, this calculation I presented today was a bit of a warm-up. It is representative of the sorts of calculations we'll be doing in this class. If you don't remember your Dirac notation, Bras and Ketz, you should probably brush up on that. If you don't remember your basic quantum mechanics, you should probably brush up on that. If there was some complex variables manipulation that was a little unfamiliar, that's not the end of the world, but you probably want to remind yourself a little bit about that. And if you have any questions or thoughts, please feel free to let me know. I do have office hours Wednesday at 3, so you're always welcome to stop by tomorrow if you have questions. Okay, see you on Thursday.